Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about metal with a memory. Picture a satellite packed into a rocket, folded like origami. It survives launch, enters orbit, and then unfolds itself. No motors, no hinges, no command signals, just a silent, seamless transition, triggered by the sunlight. This transformation is made possible thanks to something called a shape memory alloy, or an SMA. These are metals with physical memory. Bend them, twist them, deform them, and they snap back to their original form when heated, not because of springs or stored tension, but because of changes in the atomic structure itself. That property is being used right now in experimental satellite components, unfolding antennae, and future telescopes that assemble themselves in orbit. Traditional space mechanisms are bulky and prone to failure. They depend on actuators, expensive bolts, or intricate robotics. Shape memory materials eliminate that complexity. They're lighter, simpler, and in some cases, even far more reliable. In today's episode, we'll look at the atomic science behind these metal muscles, the missions already using them, and the frontier where materials don't just support engineering, they are the engineering. Spacecraft are marvels of engineering, but getting them from Earth to orbit introduces a brutal design constraint. Everything has to fit into a narrow, cramped rocket fairing. That means antennas, solar panels, radiators, and even booms need to be tightly folded or compacted, and then deployed perfectly once in space. Historically, engineers have tackled this with complex mechanical systems: hinges, motors, pulleys, pyrotechnic bolts. Every piece must perform flawlessly, often in extreme temperatures, zero gravity, and total isolation, with no possible help from Earth. And even if one actuator jams, an entire mission can fail. NASA's Galileo spacecraft lost a major science instrument when only one antenna failed to deploy. More recently, both commercial and government satellites have faced multi-million-dollar setbacks because of stuck mechanisms or mistimed circuitry. To mitigate these risks, designers build in redundancies: backup motors, extra cabling, reinforced brackets. But redundancy adds mass, and in spaceflight, mass is money. This is where shape memory alloys offer a radically different solution. Instead of building more machinery, we completely reinvent the original machinery. SMAs can be created and designed to fold or curl and then transform back into their intended shape when heated, usually just by absorbing sunlight and the heat that is associated with it. SMAs don't even use the solar energy from the sun like a solar panel would. They are a direct response to heat from any source. It's not just elegant, it's efficient, and it's already showing up in low Earth orbit satellites and exploratory payloads. The materials themselves have become the actuators, unlocking a new design language for space, one that's lighter, simpler, and fundamentally more resilient in the unforgiving vacuum above. To understand why these materials are so promising, you first have to grasp what makes an SMA so unusual. The key lies in their internal structure, which can shift between two solid phases: martensite and austenite. At lower temperatures, the alloy is in its martensite phase. It's soft, easily deformable, and can hold a new shape when bent. But heat it past a certain threshold, and the atoms realign in its more ordered, highly symmetric phase, austenite. When this transition occurs, the material recovers its original configuration with a remarkable accuracy and force. The most well-known and widely studied SMA is Nitinol, an alloy of nickel and titanium discovered in the 60s. Nitinol's phase transition is both reliable and tunable. You can design it to remember its original shape at specific temperatures, often around 50 or 60 degrees Celsius for space uses. That makes it ideal for solar-triggered deployment, where temperature swings are constant and predictable. What's remarkable is that the phase change doesn't involve melting or softening. Both martensite and austenite are solid forms, meaning the change is entirely structural, not chemical. It's metal that reconfigures itself internally without becoming liquid or losing cohesion at all. One of the most intriguing parts of the process is hysteresis, the gap between heating and cooling temperatures where the transformation occurs. Engineers can use this window to prevent accidental actuation from minor temperature fluctuations, ensuring the SMA only activates when it's supposed to. Shape memory alloys aren't just components. They're a fundamentally different way of thinking about motion, structure, and control, one where function is embedded directly into the material itself. The behavior of SMAs isn't just about temperature, though. Though that is what sets it off, it's about atoms rearranging themselves with precision. At the microscopic level, the shape memory effect emerges from a solid-state phase transformation, specifically a martensitic transformation, which is a diffusionless shift in atomic arrangement. In the martensitic phase, the structure of the material usually has its atoms slightly displaced from their high symmetry positions. This structure is highly twinned, meaning the crystal contains mirror image domains that can reorient in response to stress. That's why the material is soft and malleable during the martensite stage. The atoms are free to shift without breaking bonds. When the alloy is heated above its transformation temperature, the atomic lattice snaps into the austenitic phase, typically cubic and more symmetric, where atoms are arranged in a more stable, lower energy configuration. This shift doesn't require atoms to move long distances like it would in melting. Instead, it's a coordinated collective rearrangement, like a snap of a grid into a new pattern. What's powerful is that this transformation is reversible. When the material cools, it returns to martensite. If no stress is applied, it goes back to its original shape. But if it was bent while on martensite, the structure remembers its original geometry and restores it when reheated to austenite. The energy landscape behind this behavior is defined by thermodynamics. Austenite is favored at higher temperatures because it has lower energy. Martensite is metastable at lower temperatures, which allows it to deform easily but still store the energy needed to return when the conditions are right. Basically, when in the martensite phase, there is enough energy to eventually snap back. In a way, SMAs are like loaded springs at the atomic level. Deforming them stores mechanical energy in the lattice itself. Heating them unlocks that energy and drives the material back to its programmed shape, without any moving parts, grease, or gears. Just atoms doing what they've been arranged to do. Not all shape memory alloys are created equal, though. To work reliably, especially in the demanding conditions of space, an SMA needs more than just phase-changing ability. It needs to survive radiation, thermal extremes, vacuum exposure, and mechanical fatigue. That's why the choice of the material matters. The gold standard in SMA research is Nitinol. Its appeal lies in a unique combination of strength, corrosion resistance, and a well-defined, repeatable phase transition. Nitinol can recover stretches up to 8%, 16 to 40 times beyond what most metals can do without permanent deformation. It also shows excellent fatigue resistance, critical for repeated actuation cycles. This number means that a 100mm Nitinol wire can be stretched to 108mm without suffering any consequences. But Nitinol isn't the only option. Other alloys, like copper, aluminum, nickel compounds, and iron, manganese, silicon compounds have been developed for specific applications. Copper-based SMAs are cheaper and easier to process, but they tend to be more brittle and degrade faster under thermal cycling. Iron-based alloys are more robust and cost-effective, but their shape recovery is less precise. Key properties engineers look for in these materials include temperature deformation range. It must be compatible with the thermal environment of space, often in the 40 to 100 degrees Celsius range. Recovery strain. The higher the strain the material can recover from, the more work it can perform. Fatigue life. How many actuation cycles the material can survive before losing function, and more. New research is also focusing on SMA composites, where shape memory wires or films are embedded in lightweight structures for added strength and flexibility. These next-gen materials are being tailored for specific missions, with custom transformation profiles, longer service lives, and improved energy efficiency. In space, where every gram and every failure counts, the right alloy isn't just a preference, it's mission critical. Shape memory alloys have advanced far beyond the laboratory, proving their value in actual space missions and satellite technology. Engineers at NASA, the European Space Agency, and commercial entities have integrated SMAs into rocket components to create lightweight, reliable, and autonomous deployment systems. One of the earliest space applications was NASA's Deep One space mission in the 1990s. which used SMA components for solar array deployment, demonstrating early confidence in this technology for critical operations. Building on this, NASA developed the SHUMLA program, or the Shape Memory Alloy Ultra Lightweight Actuator program, producing compact SMA actuators for antennas and microphones. These actuators use Nitinol wires that contract when heated, often via electrical current or sunlight, pulling structural elements into place without mechanical motors or gears. The European Space Agency has employed SMA-based release mechanisms for small satellites, using thin Nitinol wires to trigger the deployment of solar arrays and antennas by contracting upon heating. These systems replace traditional pyrotechnic bolts or complex mechanical latches, offering quieter, reusable, and shock-free actuation. The commercial sector has embraced SMAs, particularly in CubeSats and small satellites. University projects and startups increasingly rely on SMA hinges and release devices to deploy solar panels and communication antenna. The simplicity, reduced mass, and reliability make SMAs attractive for cost-sensitive and compact missions. More recently, the European Space Agency's Proba-3 mission, a formation-flying satellite designed to study the solar corona, used SMA actuators for deployable microphones and precise structural unfolding, critical for its science objectives. NASA's Artemis 1 mission also incorporated SMA technology in some deployable elements, reflecting growing institutional trust. SMAs are also tested for thermal management, using their phase changes to passively regulate temperature, protecting sensitive spacecraft components from harsh thermal swings. Field tests have demonstrated that SMAs maintain performance despite extreme temperature fluctuations, vacuum conditions, and radiation exposure. Their ability to remain dormant for extended periods before activation makes them ideal for long-duration missions where components may stay inactive until deployment. Together, these real-world missions confirm that SMAs have transitioned from experimental materials to essential parts of spacecraft design. They reduce mechanical complexity, cut mass, and increase reliability, attributes critical as space exploration grows more ambitious. Looking forward, SMAs are poised to play an even bigger role, not only deploying structures, but enabling adaptive, self-regulating spacecraft capable of responding autonomously to their environments. A remarkable synergy is emerging between shape memory alloys and origami-inspired engineering. The art and science of folding structures into compact forms that later expand or unfold. This combination offers a way to pack large, functional components into small rocket fairings, then deploy them precisely in orbit. Origami principles allow engineers to design solar panels, antennas, and even habitat modules that fold like paper cranes or intricate tessellations. The challenge has always been reliable unfolding, though. Traditional hinges and motors add weight, complexity, and potential points of failure. Enter shape memory alloys. By integrating SMAs into fold lines or hinges, these structures gain a built-in, heat-triggered unfolding mechanism. When exposed to sunlight or an electrical pulse, the SMA wires or strips contract or bend, driving the structure to unfold and lock itself into the desired shape. One study published in the journal Science demonstrated programmable folding sheets made by shape memory polymers, cousin to SMAs, that can be programmed to fold into complex 3D shapes upon heating. Though not metallic, this work hints at the potential for SMA-based materials to achieve similar self-assembly, but with higher strength and durability. Practically, this means spacecraft can carry larger, more capable instruments or solar arrays that can fit in tiny packages during launch. Once deployed, these structures gain the rigidity and precision needed for scientific measurements or power generation, all thanks to materials that combine folding geometry with thermally activated motion. This fusion of ancient art and cutting-edge material science is redefining how we think about building in space. Not just assembling, but programming materials to move and transform on their own. SMAs bring remarkable advantages, especially for space applications, but they also come with notable limitations that researchers and engineers must carefully manage. In terms of their strengths, SMAs are prized for their ability to change shape and recover that shape repeatedly, without complex mechanical systems. This repetition reduces mass, increases reliability, and simplifies spacecraft design. Their ability to transform triggered by heat, often just sunlight in space, means deployment mechanisms can be passive and autonomous, requiring no motors, lubricants, or electronic controls. This significantly cuts down potential points of failure and maintenance needs. Despite these strengths, SMAs have several inherent challenges. Firstly, fatigue and durability are major concerns. Repeated heating and cooling cycles induce microscopic structural changes that gradually degrade the material's performance. For long-term space missions, ensuring SMAs retain their functionality over years or decades remains an active research area. Secondly, controlling the activation temperature precisely is critical. Space has extreme thermal environments where unintended temperature fluctuations risk premature or failed actuation. Designing robust thermal management systems is essential to avoid these problems. Third, the strain recovery limit of around 8% for Nitinol, despite being much higher than most other SMAs, is very low, and this constrains how much movement an SMA can produce alone. Larger deployments usually require hybrid systems combining SMAs with traditional mechanical elements. From a manufacturing standpoint, producing consistent, high-quality SMA components at scale is difficult. Small variations in alloy composition or heat treatment can shift phase transformation temperatures and mechanical properties, demanding tight process control. Radiation exposure in space may also induce material changes, potentially affecting long-term behavior. While some data exists, more extensive testing is needed. Finally, SMAs like Nitinol are more expensive than standard metals. Though their benefits often outweigh costs for critical applications, budgets and manufacturing complexity remain practical barriers to widespread adoption. While shape memory alloys alone are impressive, researchers are exploring ways to combine them with other smart materials to create multifunctional systems that can sense, adapt, and respond dynamically. One promising direction is embedding piezoelectric materials alongside SMAs. Piezoelectrics generate electrical signals when mechanically stressed, allowing structures to monitor strain or damage in real time. Integrating them with SMAs creates a feedback loop. Materials that not only move, but also feel their state. This could eventually lead to adjustments based on specific stressors that SMAs might experience. Another innovation involves shape memory polymers, which deform and recover shape like SMAs, but with lower density and easier processing. Hybrid composites using SMPs and SMAs can tailor stiffness, recovery speed, and temperature response for specific space applications. Researchers are also developing self-sensing SMAs by incorporating conductive nanomaterials, enabling the alloys to track their phase changes electrically. This could provide astronauts and mission control with continuous data on deployment status without adding bulky sensors. Finally, the integration of nanoscale electronics or microcontrollers with these materials could enable autonomous adjustment, allowing structures to respond intelligently to temperature, stress, or damage, all without human intervention. The marriage of material science and electronics points toward a future where spacecraft components are not just passive building blocks, but active, intelligent systems, capable of self-monitoring, self-adjusting, and ultimately self-healing. Looking ahead, the potential applications for shape memory alloys in space and beyond are expanding rapidly as research deepens and new alloys and composites emerge. One exciting frontier is the development of large-scale deployable habitats for long-duration missions to the Moon, Mars, or deep space. SMAs could enable modules that arrive compactly folded, then autonomously unfold into pressurized living spaces without heavy mechanical systems. This would reduce launch mass and complexity, making human exploration much more feasible. Another area gaining traction is space telescopes and antennas. Future observatories require massive mirrors and reflectors that fit inside launch vehicles tightly. SMA-driven deployment could enable ultra-lightweight, precisely shaped surfaces that unfurl in orbit, dramatically increasing aperture sizes without added mechanical complexity. Beyond space, SMAs have promising roles in robotics, medical devices, and wearables. The same atomic transformation that enables satellite antenna to unfold are being used in stents, orthodontic wires, and even soft robotic grippers. Their biocompatibility and unique mechanical properties open doors for minimally invasive surgeries and adaptive prosthetics. Back in space, the next generation of SMAs might be multifunctional composites, materials that not only change shape, but also conduct electricity, sense damage, or self-repair microcracks. Coupled with AI-driven control systems, these materials could enable spacecraft that adapt dynamically to changing environments or damage, extending mission lifetimes and reducing maintenance needs. Research into high-temperature SMAs is also advancing. aiming to push activation temperatures beyond 100 degrees Celsius, opening up applications in hotter environments like Venus missions or industrial settings. In short, SMAs are evolving from niche actuators into foundational components of adaptive, intelligent material systems. As understanding of their atomic behavior deepens and manufacturing techniques improve, metal muscles may well become the standard toolkit for building the resilient, lightweight machines humanity needs to explore and thrive in space and on Earth. Today we uncovered how shape memory alloys, these metal muscles, are transforming space engineering by enabling lightweight, reliable, and autonomous structures. From atomic scale changes to real missions, SMAs offer a new way to build smarter, adaptive spacecraft. Though challenges remain, advances in materials, sensing, and AI are pushing this technology forward. Soon, shape memory alloys won't just be parts, they'll be active living components powering exploration.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.